Good. Okay, so 2.3 is all about continuity at a point, which we've already talked about. What does it mean to be continuous? So what do we need to have? You need to have the left and the right limits equal and the actual value. But we can also have continuity at an endpoint, and that just means, sometimes we'll look at a function and I'll have like a starting and a stopping point, or because of the domain. So if it's continuous in the interior, then that has to be true, right? And as soon as we see this, that means your left and right hand limits are matching. And then if it's continuous at an endpoint, then we have a one-sided limit, right? So if it's continuous at a left endpoint, then from the right. Does that make sense why it's like opposite? Because if it's on the left, we have to approach it from the right. And then if it's a right endpoint, we have to approach it from the left. Yeah, see it? Okay. And if it doesn't, we have a point of discontinuity. Just a quick reminder, C does not need to be in the domain. Okay? For example, back to this function. Where's the discontinuity? Okay, x equals 0. What kind of discontinuity is it? Infinite. Is 0 in the domain? No. Does that make sense? So it's an infinite discontinuity at 0, but 0 is not in the domain. And that's okay. All right. Good. Questions? Need anything clarified? Okay. All right. Let's find for this piecewise function a value for a so that the function is continuous. Okay, so if we were going to do this on a free response question, going back to the definition, what do we need to show? Yeah, right.
They meet from the left and the right.
They meet from the left and the right, and the actual value is going to be the same. So let's show that. So what are we going to do? We're going to show limit as x approaches 2 from the left of f of x. Okay, so we're using that formal definition. What are we going to get? Okay. I'm not trying to trick you. It's just, okay. Now let's do the limit from the right. And we get 2a plus 1. And we're also going to make sure, I'm just going to write this down, f of 2 also equals 7. So all three of those things must be equivalent, right? So all I really need to do is show 2a plus 1 equals 7. So we get what for a? Good.
How can you prove that f is 7?
Oh, you want to, if you plugged it in, right? Because it's less than or equal to.
Yeah. Oh.
So technically,
So if
I plugged in here and here kind of the same.
would it not be continuous if that wasn't the case? If both of those were like there was no equal in either of the.
Oh, if it didn't have an equals, then it would not be possible.
Okay.
So basically what we're saying is now our function, you don't have to write this, you don't have to write it, but just so you can kind of think about, right? So we solved for a, we said that was x.
Right. Okay.
So therefore, this is continuous. You don't have to write that, I'm just showing you, right? Now we can easily see if we were to plug in 2 here and here, do we get the same value? Yeah, that's what we wanted. We get 7. Okay.
When we're doing it on the test, do we have to write out the entire thing, or can we just make them equal to each other?
You can just make them equal to each other. Okay? Yeah, Maya.
Do we need to write a limit when we're setting 2 of this one equal to 7, or is that?
is that, I think, that's kind of like what Molly was asking? You don't have to show it. You could just set them equal to each other. I just wanted to make sure you had it as well. If I asked you to prove it, then you have to use the limit, okay?
But you wouldn't have to write a limit in front of that last part that you did.
The last part. Oh, you mean this part here? Is that what you're talking?
2a plus 1 equals 7.
Oh, no, you don't need limits there. That's fine. Okay, we already talked about this, right? Removable jump. What's the difference? Like in terms of limit, what's that mean for removable discontinuity? This is when the limit from the left is equal to the limit from the right, but not equal to f of 0. Sorry, not a lot of space in there. We did that, I think, when we reviewed the summer packet, didn't we? I feel like we did. So when the limits are equal, but it's not equal to the value. What's the difference with the jump discontinuity? Well, what's in terms of the limits? From the left, they're not equal to each other, right? And finally, the infinite discontinuity, that's when it goes to positive or negative infinity, basically vertical asymptote. Not a horizontal. Horizontal's different, right? Vertical, it's got to be infinite. Okay, find the intervals of continuity and the points of discontinuity of the function, and then we want to identify each type of discontinuity. I just have one example. What should we do? Mayan?
Yeah, I would say vertical asymptote.
Okay. So x equals 5 is a point of discontinuity, right? And we said it's infinite. Or did we say it's infinite? You said vertical asymptote, so. And the last part was actually the first part I asked for. Where is it continuous? Negative infinity to 5. Do we use brackets or parentheses? Parentheses, good. And then 5 to infinity. Good. Questions on that?
Would it be like numbers in between? Oh wait, never mind.
If you had multiple vertical asymptotes, or if you had, let's say you had a removable discontinuity where you have something cancel and you have a vertical asymptote, you can have, you can have infinitely many points of discontinuity. I wouldn't give you more than, 2 to 3. One thing I also forgot to mention just real quickly, we also want to consider the domain. So I believe we had, let's say it was a natural logarithm, right? So natural log of x. I think we briefly talked about that. That doesn't have, even though there's a vertical asymptote involved, that's not a discontinuity. There's not another part to the graph, right? It's just that curve, right? Good. All right. This is just this is intermediate value theorem. This is technically one of the 4 big function or theorems in calculus, but you technically learn it in pre-calculus. Have we learned this? Maybe. And we abbreviate it. Intermediate value theorem. Okay. It looks like a complex theorem. When you try to read it, you're like, okay, continuous on a closed interval takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c. Okay, great, whatever. Basically, you're saying, okay, here's a, here's b. You got a closed interval. So that means if it's, here's the most important part, it's continuous on a closed interval. Okay, so I know we're not doing geometry anymore, but we still have theorems. And on the AB exam and in this class, you have to be able to justify why you're applying something. So we would have to say, by the intermediate value theorem, this must be true. So they're basically saying, if this is continuous, here's f of a, right? Here's f of b. That means it must take on all the y values in between. It can't jump over a value, right? Take like you're driving. Okay, you drive from home to school. Can you live in Encino. Can you skip over Tarzana? Well, I guess you could go around it, but you're still covering all those places around. So you can't jump over. It's a continuous function. That's really all it's saying. So how would this be applied? Let's say I gave you the function y equals x squared. Give me a domain. I don't really care what it is. 2 to 8. Great. Okay. So I want to show at some point, let's see. So will y equals x squared, or I should say, will y equal 30 at some point in the interval? Okay. Okay. So what's f of 2? 4. And f of 8 is 64. So at some point, according to the intermediate value theorem, it has to be 30. It also has to be 31. It also has to be 31.2, right? And so on. It has to have those values. So, yes. And we can use abbreviations on the FRQs. You could just say, you would say f of 2 equals 4 and f of 8 equals 64. So therefore, by the intermediate value theorem, it has to equal 30 at some point. Yeah?
Can't you you can't really say no for sure though, right? Because in this example, for example, it goes over
Oh, yeah.
the c-value.
Okay, so that's a perfect. So it could go beyond those values, but all we can justify is between these two values. So, for example, can I justify that y will equal 100? No. Could it equal 100?
Yeah.
Yes. It could go above 100, right? But which obviously y equals x squared does go past 100, but according to this, we cannot justify it. Okay? Yeah, Mayan.
And if there was a removable discontinuity,
then the theorem no longer applies. Okay? So we cannot apply this theorem to a function that has a discontinuity. So we'll learn different theorems in this class. Some just require continuity, others require something called differentiability, but you need to make sure that that's true before you apply the theorem.
But even if, let's just say there's a removable discontinuity on the one that we were talking about, even if it's before y equals
Okay, that
30,
doesn't matter. So if there was a let's say
but if it's within the interval, but
yeah. So if I have an asymptote over here, I don't care.
What if there was a discontinuity in between 2 and 8, but it wasn't what you were looking for?
Then you still can't.
Okay.
You can't apply it.
Oh, you can't.
No, it must be continuous on the closed interval.
But wouldn't if there was a removable discontinuity in between that interval, it wouldn't have an impact on the answer necessarily, right?
It doesn't matter.
Okay.
It doesn't matter. As soon as you have a discontinuity, the theorem doesn't apply.
Okay.
Okay, even if it's removable and you think just one little point missing shouldn't matter, it does.
Okay.
Okay, good. All right. Next page, 2.4, rates of change. And we've also talked about this, average rate of change. Look good. It's over a period of time. But you can also find an average rate of change on just any graph, just using, what is this? This is just slope. That's all it is. right, slope. Okay, so let's find the average rate of change of the function over the interval. You can do this, right? Okay. Oh, you got it? Okay. It's only cube root of x. I know, again, then I make it sound so easy, and then you're like, I forget to. 1/7? Cube root of 8 minus cube root of 1. Perfect. Okay. What does that mean? If you're trying to explain that, what's 1/7 mean? Can you explain it, Mia?
So it's like up 1 and over 7 on the graph.
Okay, so the slope or the average rate of change on that cube root in the interval from 1 to 8 is 1/7. It's the average rate of change. Now, that means what? Some places, well, what's cube root of x look like? Looks like that. So it's saying from 1 to 8, that slope, right? That was not a good secant, but you get the idea, right? That slope, that average rate is 1/7. Sometimes it's going to be steeper, has a steeper slope, and sometimes it's going to be less than 1/7. And here we just kind of spell it out. Secant slope is just what we did. Secant slope and average rate of change are the same. Okay. Tangent. Oh, Maya.
Another question.
Yeah.
So okay, well, what's the difference between the secant and tangent slope on the actual graph?
Okay. The secant needs 2 points. Okay. Think if you remember back to geometry and circles, we did secants that go through the circle, and then tangents just touch the circle at one point. That's the difference. So tangent, okay, imagine, right, here we have 1 and 8. What if we were able to slide, right, 8, this line, and get closer and closer and closer and closer to 1? Again, that limit gets to be 0, approaching 0. That would be your tangent.
The tangent only hits 1 point.
Only hits 1 point. Perfect. Good? So here's your tangent slope, which is, you know, if I ask you to find the slope of the curve, that's the same thing as the tangent slope. This is your limit as h approaches 0, right? That f of, and you can also write x and a in this scenario are interchangeable. So if you prefer working with x, which sometimes I do, it's just a preference. Okay, let's find the slope. And we're going to find it at -2, 2. And then we're going to write the equation for the tangent to the parabola at that point. Okay, so find the slope. So m equals, don't forget to write the limit. We always want to keep writing the limit until we actually are able to evaluate it, okay? Okay, what are we plugging in?
Can you plug it in afterwards?
You could plug it in afterwards. Do you want to just come up with the formula and then plug it in? Perfect. Okay, so I want x plus, are we okay if I use x?
Yeah.
Okay, minus x plus h minus x squared minus x. If you distribute, yes, totally fine. Good, look good? All right, keep going. You want to try this one? How's it going? Good. Can you follow some of it? No? Oh. Is it more language, or you think it's just different? Both. It's hard because our math is so different. I know. They used to have a math teacher that would come. Uh-huh.
Oh wow.
Yeah. Yeah, absolutely. Does it say slope intercept? No. So, okay. Remember, if you can't get h to cancel, then we made a mistake somewhere. The whole idea is at the end, you should just have something in terms of x. And then if you have the slope, go ahead and write the slope intercept. Ryan. Yes. Did you do it right?
Yeah.
So are you
Well,
saying
up to this point, not like I'm not finished.
you're not finished? Okay, good, because that's not finished. I think we're missing something. I think you're missing a term somewhere. Did you get the resulting? Did you get 2x minus 1?
There you go.
Yeah.
I just plugged
Sure.
in negative 2 0.
Oh, okay. Okay, let's see. I don't know if I can squeeze it in here. So you should have x squared plus 2xh minus x minus h minus x squared plus x. Yeah? Did I forget the h squared? Thank you. Okay, all over h. See, I was writing so small that I can't even see. Then what? The x squareds cancel. The minus x and the plus x cancel. So we're left with, okay, so we have 2xh plus x squared minus h all over h. Yeah? What? I was looking for your approval, that's all. Okay, what can I factor out? H. I prefer to see the step factoring out h rather than just canceling it because I see so many mistakes. Right, now we can cancel. Now we can actually evaluate it, right? So we end up with 2x minus 1, and that is the equation for our slope. Good? What's our actual slope? So this implies that m will be 2 times negative 2 minus 1, right? Plugging in our x coordinate. So that gives us a slope of negative 5. You want to think about sometimes, does this answer make sense? So think about what you would have here. You would have an x squared minus x. That's a parabola, right? So at negative 2, 2, would you have a tangent slope of about negative 5? Yeah, that makes sense. And you can, maybe do a quick sketch to make sure that answer makes sense. It wouldn't make sense if that was a positive 5. Why? It's like this, and it's like over here, right? So it is helpful to just think about, does my answer make sense? Yeah, Molly.
I'm still a bit confused on what, so I got this answer as negative 5. What is it, what is a tangent?
Oh, that's what that's what I was just talking about. So what does x squared minus x look like? Well, it's a parabola. Here, maybe I'll sketch it here. What are the zeros? Sorry, let's say, because you have to be able to sketch these things on the AP exam pretty quickly. You're not going to have really crazy, intense ones, but you should be able to say, oh, I can just factor that real fast. Or maybe you can complete the square to find the vertex, whatever. I see that I have a 0 at 0 and at 1. Right? So it's going to be, oh, sorry. Whatever. Really quick sketch. Yeah? So at negative 2, let's say here's negative 2. That's a very sloppy picture, but hopefully you get the idea. What is that tangent slope going to be? Negative 5.
So it's like an imaginary line?
Yeah. I'll show you on our calculators when we get to it later. Not now. I don't want. You can actually graph this, and you can draw the tangent line. There's a button in the menu to draw the tangent. Yeah, Ryan.
So the answer is n equals negative 5, or do we?
Okay, there's two parts. There were two parts. Find the slope. Okay, we did. I'm going to circle that. Okay, so when like on homework, if it asks you for multiple, like find the slope, circle that, find the tangent line, that's just the second part. And do we have to do point or slope intercept? Nope. So I'm just going to write it as, oops, that's a minus. Y minus 2 equals -5, and then x plus 2. So this is my there's my tangent line. And if you wanted to get a real visual, sorry, here you go, Molly, I see you. You can graph the function and you can graph that line and you can easily just see it right on your calculator that that does make sense. If you have a calculator available for, this would be a non-calculator problem though. Okay. Good. We got one last question, and this is again revisited because we've done it. What is this? It's the same equation we just did. It's just a different format because I use t instead of a or x. That's all. Okay, speed of a falling rock with position y equals 16t squared at t equals 1. Okay, so do we want to plug in t to start, or do you want to find the formula again and then plug in t? You like finding the formula and then plugging in? Okay, just so you know, I have no preference. I prefer to plug it in because I think it's easier, but if you're used to finding the equation and then plugging in, go for it. So I'll since you're used to, because I know Mrs. Malikian taught it both, but did a heavier focus on keeping the formula, right? Yeah. Now. Okay. Shall we give this one another try on our own? Okay. I did freeze it, right? Okay. I was going to work out the solutions ahead, so sometimes I forget.
Units for this one, or can I just write like units per second?
Yeah, don't worry about units. If they gave you, if we gave you, distance and rate of time, then include it. If not, you can just leave it as the answer. It's okay. I wrote out a lot of steps here. Oh, okay. What'd we get for the rate? 32. Okay, so this implies, right, 32 times 1. Okay. If I don't give it to you, I didn't say what it was. I guess I did give you a second. So units per second. I don't know. I'll make sure to give you like feet per second or whatever it might be. Okay.